In this video, we're going to explore the question of whether a certain polynomial is irreducible from several different points of view. So I've put this question here: is the polynomial 3x squared plus 6x plus 15 irreducible? And one thing we're going to discover in this video is that the answer to this question depends on the following question. In what setting are we talking about? So is the setting something like z bracket x, because this polynomial makes perfect sense as a polynomial in z bracket x, or could it be in q bracket x? Or are we talking about irreducibility in a much larger polynomial ring like c bracket x? The major lesson of this video is going to be that considerations of whether an element is irreducible depend upon things such as what are the possible factors and what are the units. And that's going to lead to different answers here and here and here. Well, I guess they can't all three be different answers, because the answer is either no or yes. So two of them, by the pigeonhole principle, at least have to be the same. But we're going to find that this problem works out a little bit differently in each case. All right, so let's start with z bracket x. So one thing that you learned in grade school is that if you have a polynomial like 3x squared plus 6x plus 15, one thing that's always useful to do if we're thinking about how to factor the polynomial is first look for any numerical factors that we can pull out of each of the coefficients. So in this case, we see a 3 and a 6 and a 15. That just calls out for us to factor out a 3 before we even get started thinking about the rest. So we have 3 times the quantity x squared plus 2x plus 5. At this point, you might start to think, this doesn't look factorable, but actually, we've already answered the question of whether this polynomial is irreducible in z bracket x. The reason for that is because, what does it mean to be irreducible? Irreducible means if a ring element is factored as a product of two other ring elements, then one of those elements has to be a unit. And when we look at what we have here, this factorization of 3x squared plus 6x plus 15, so it's 3 times x squared plus 2x plus 5, and we consider the fact that we're in z bracket x, well, 3 is a polynomial in z bracket x. It's just a constant polynomial. And it's not a unit because when you think about what we would have to multiply by 3 to get 1, the multiplicative identity, the inverse would be just 1/3. And this is not in z bracket x. So 3 is not a unit. And that's crucial here because that means that now I've factored 3x squared plus 6x plus 15 into one element, 3, another element, x squared plus 2x plus 5. That is definitely not a unit. Neither of these is a unit. Therefore, since neither of these is a unit, therefore 3x squared plus 6x plus 15 is not irreducible. It is reducible. And you might say, well, it's reducible in a stupid way, but it doesn't matter. We've factored it into two ring elements, neither of which is a unit. So that means that in z bracket x, this polynomial is not irreducible. All right, so let's proceed to think about q bracket x, because that's going to be a little bit different now. So I'm going to start the same way. 3x squared plus 6x plus 15 equals 3 times the quantity x squared plus 2x plus 5. And you might say, that's still a factorization. It still works over q. So nothing really changed in jumping from zx to qx because my factorization still works. But actually something did change, because now my factorization consists of 3, x squared plus 2x plus 5. This is still a non-unit. A polynomial in a polynomial ring, a polynomial of degree 2 is never going to be a unit because there's nothing we can multiply that by to give 1. But 3 is very much a unit because its inverse is 1/3, and 1/3 now belongs to the polynomial ring. So this is now a unit, and this is a non-unit. Okay, so just a word of caution, that does not mean that my polynomial is irreducible. It just means that I haven't found an interesting way to reduce it yet. But there could still be a way out there. We still have to look for one. All right, so the way we're going to approach that, one thing you might consider is you might think, well, if there is a way to reduce it, then there must be a way involving this polynomial here. There must be some way to factor this. But I'm going to take a naive approach and not assume that we know that for sure. I'm just going to say, well, let's see if we can find a way to factor this. All right. So I'm going to ask, does this factor into ax plus b, cx plus d, where a, b, c, and d are rationals? And my thinking here is, if this degree 2 polynomial is going to factor, it's going to factor either into kind of like what I have here, a constant and a degree 2, in which case the constant is going to be non-zero and therefore a unit. So that kind of factorization isn't really going to shed any light here. Or it's going to have to factor into some linear times another linear. Those are the only two options for how this is going to factor. This one's never going to lead to an interesting factorization, so I have to count on this. All right, so can I factor this into ax plus b, cx plus d? And there's a couple of ways I could try to approach that. I could try to figure out some combination of coefficients like a times c equaling 3, b times d equaling 15, and then ad plus bc equals 6. Keeping in mind that those could be rational numbers. They don't necessarily have to be integers. I could do all of that work, but I'm actually going to try a different approach. So here's the idea of my approach. If it is true that 3x squared plus 6x plus 15 equals ax plus b, cx plus d, if that were true, well, the polynomial on the right is going to have a couple of roots, and those roots will be rational. There's going to be a rational number x that makes this 0. There will be a rational number x which makes this 0, because remember, a, b, c, and d, they're all rational. So if that's the case, then this is going to have one or maybe two different rational roots, which means this will also have to have rational roots. And I think I can show that that's not going to be the case. Now I'm going to use mathematics that we haven't formally proven yet in this course, but that we know pretty well from high school. We know that there's a quadratic formula that will tell us what the roots are of this polynomial. So what would the roots be? The roots will be x equals -6 plus or minus the square root of 36 minus 4 times 3 times 15. 36 was 6 squared. Over 6, that comes out to -6 plus or minus the square root of, what is 36 minus, I think that's going to be negative 144. 36 minus 180 all over 6, and that comes out to -1 plus or minus the square root of -4, which is -1 plus or minus 2i. So yeah, verily, this polynomial does not have any rational roots. It does have roots in the complex plane, but those certainly don't lie in Q. So this is going to be impossible because, again, if this did factor into two linear polynomials, each of those linear factors would give me a rational root, and I simply don't have any. So to recap, this polynomial does not factor in an interesting way into a constant times a quadratic, because that constant's always going to be a unit, and it doesn't factor into two linears. Therefore, this polynomial in Q bracket x is irreducible. Okay, so we've talked about zx and we've talked about qx. That leaves cx. So let's try that one now. Okay, so what about in cx? And I'm leaving the other work visible because we're going to use that to start our analysis here. We have 3x squared plus 6x plus 15, same as before. And this time we know we have two roots. Those roots are -1 plus and minus 2i. So if I allow those to be coefficients of polynomials, which I am doing in C bracket x, then by the factor theorem, because -1 plus 2i and -1 minus 2i, those are both roots. These two linear polynomials, x minus -1 plus 2i and x minus -1 minus 2i, both of these have to be factors. And you might guess, well, so that must mean 3x squared plus 6x plus 15 equals, what is that? That's x, that comes out to plus 1 minus 2i, and then x plus 1 plus 2i. Sorry about that, that's a little small there. But you'll notice that there's a problem here. The polynomial on the left has a lead coefficient of 3. The one on the right has a lead coefficient of 1. It's just x squared here. So whence the discrepancy? Well, the thing is, I'm not taking into account the fact that this polynomial has a lead coefficient of 3. In fact, a 3 factors out of the whole thing. I think if I put a 3 there, then I will be in business. And you can actually check that if you multiply all this out, you really do get 3x squared plus 6x plus 15. I'll spare you the rampant use of the distributive property, but you can check that for yourself. So we do, in this case, have a factorization. Now, in this case, 3 is still a unit. 3 is still a unit in Cx. However, this is a non-unit, and this is a non-unit. And if you want to stick to the letter of the law and say that being reducible means that you factor into 2 elements, neither of which is a unit, then let's just jam these two together. 3 times x plus 1 minus 2i, so call that 3x plus 3 minus 6i. That's one of your factors. Your other factor is here, and neither one of them is a unit. So that means that this polynomial is not irreducible, but for a totally different reason than before. So what that goes to show is that you have to be really careful about questions of whether a polynomial is or is not an irreducible element of a ring. You have to be careful about which polynomial ring you're in, and particularly about which things count as units, because here 3 was a non-unit, which made it an interesting factor, while over here 3 was a unit and therefore not that interesting. So we had to find other factorizations or show that we couldn't. So anyway, that is an introduction to the question of whether polynomials are irreducible. More later.